Alright, so I got, you guys hopefully remember this from when I had the levers out. I was showing you the lever. And so this meter stick is going to be free to rotate around this point. So if I put it on this fulcrum here, right, the meter stick rotates about this axis. Everybody see that? Okay. What I'm going to do is I will hook a clip on this end, here, another clip on this end, and let's see here. It's about balanced a little bit, not quite.
No.
And so that is at about the, well, this is exactly at the 50 centimeter mark here. And then this is at about 71 something. And this is at, 29 something, 28 something. So for our intents and purposes, they're equidistant. Okay, equidistant. That way the meter stick's balanced. And each one of these is 20 grams. So I'm going to hang 20 grams from each one. Probably not perfectly 20 grams, but good enough. Okay, they're balanced. So which one is applying more force? This one or this one?
Equal, right? Left side. Yeah.
Why are you saying that?
It's going in the positive direction.
Magnitude. Let's talk about magnitude.
Same.
Same, right? Same force. I do have more masses here. So let's say that I wanted to get it to rotate clockwise for you guys by applying another mass. Will I hang it here or here? Second one, right? So if I'm going to hang, this is another 20 grams, right? Right now it's 20 and 20. We're not rotating. I'm going to put 20 grams on here, and then it's going to rotate, hopefully. There it is. Okay, there. So I did it. What do you mean? I put where is there more force now? This side or that side? This one or two? One, right? There's more force over here because there's more weight. How much more force is here than here? Twice as much, right? So there's twice as much force on this side than on this side, yet it's not rotating. Because what else did I do? I moved this one out, right? So how much further is this one from the axis than this one? Right, this one's twice as far as this one. Twice the force, half the distance, half the force, twice the distance, no rotation. So it's not only force that causes an angular acceleration, right? Because if I move this one way or the other, we will get an angular acceleration, right? Let's leave things as they are. And what I want to do is get it to rotate this way. So let me tighten these down first. A little bit. Still. Alright, I want to get it to rotate that way. Counterclockwise for you guys. But I want to do it by moving this. Which way am I going to move it? This way? So to your left or to your right? I'm going to move it to your left. And that's going to make it allow it to do that. it out to the right past the point it originally was at, then it'll rotate that way, right? Okay. Bring it back to the original place, and we balance again. So how an object rotates, or the ability to change its rotation, right, to give it an angular acceleration, depends on how much force you're applying, but also the distance that that force is applied, right? Okay. Does anybody know what that quantity is called? Because it's not force. Right? That's the quantity I'm looking for over there. It's force with the distance. It begins with T. Huh? It is torque, right? Torque. I'm going to, in each one of these pictures, we're looking down on the door. So the door, here's the hinge, and the door is rotating. It's free to rotate like that. All right. First, we'll push the door here. So that's supposed to be perpendicular. Okay, so that force, we'll say, is 10 newtons. And then we're going to push the door like this. Force is 10 newtons. And then we're going to push the door like this. Force is 10 newtons. And then we're going to push the door here. Force is 10 newtons. And then we're going to push the door here. Force is 10 newtons. Okay. So 5 different scenarios for pushing the door with a 10 Newton force. Now the first thing the slide says is you want to draw a line of action, collinear with the force. Collinear means right in the same line. So I'm going to do that with the green marker. So my line of action is just going to go in line with the force. There. And then I'm going to do it here. There we go. Line of action. We'll do it here. Action, do it here, line of action, and then we do it here, goes right through the force here, line of action, okay. So that's how you do that, okay. Now, next is the lever arm. You want to identify a lever arm, which is distance. Okay, the lever arm is the perpendicular distance from the axis to the line of action. So I'm going to draw that in blue. So let's start with this one. I go to the axis, and I'm going to draw a perpendicular line to my line of action. So that means I got to go right here, right? Because my line of action is over here. So this is going to be this terrible blue line, perpendicular line. There. That is my, what we call a lever arm. Come to this axis, where's my line of action? Here. Draw a perpendicular line to your line of action. There, make that perpendicular. So that is my lever arm. Let's go back to this one. Where is my line of action relative to the axis? Is here, so it is drawn right here. So this is my lever arm. Here, axis to the line of action. This is my lever arm. And where's my lever arm here? Axis to the line of action. Right, the line of action goes through the axis. So my lever arm equals 0. And there is no distance between the two. So now we've identified line of action, and we've identified lever arm. Right, the line of action and the door. So theta is right here, theta is right here, theta. There is no theta. Theta is 0 here. And here as well, theta. Theta is 90. So theta is always going to be between the line of action and the object that you're rotating. Okay. So now let's do Fr sine theta here for this guy. So torque is Fr sine theta. So the force is 10. R is 2. What's sine of this angle? 90. Sine of 90 is 1, right? So it's 20 newton meters. Let's do it for this guy. And let's say that theta here is 70 degrees. We'll make theta 70. So the torque, Fr sine theta, so that's 10 times 2 sine 70. Anyone have a calculator? Was it? 18.8 newton meters. Do it for this guy. Fr sine theta, so that's 10 times 2, and again, if I made this angle here 70, then we're in here, this would be 70 as well. So it's going to be sine 70 also, 18.8 newton meters. Torque of this guy will be 10 times, let's say that this distance was 1, so 1 sine 90, or 10, and then the torque here would be 10, R is 0, sine of 0, so no torque. So no torque, no rotation, minimum rotation, middle amount, these are both going to be the same torques. So they'll result in the same magnitude of rotation, and this is the maximum torque. First thing is draw what? What's the green line I drew? Line of action. Okay. That's going to go collinear with the force. So here's my line of action. Right, in line with my force. Okay, so this is my line of action. Then from there, I want to draw the lever arm. To do that, you start at the axis and you go so that you draw a line that will be perpendicular to your line of action. So here, start at the axis, draw a line that will be perpendicular to my line of action. So there's that. Now remember, my angle is going to be the angle between the line of action and R, or the object I'm rotating. So I actually want that angle. Okay? So that's the angle you want, because this is what you want to know, this length. So tau equals F R sine theta. Remember, and R sine theta is the lever arm. So if you could do the drawing, if you can draw the lever arm right, Alex, what you did was you made sine 40, right?
Yeah.
But if you drew it, you would see this is what you want. You could have used cosine 40, right?
Okay, yeah.
Because R sine theta is going to give you this length. So this is 50 here. So we're going to do 45 is the torque we want, F, and then R, 0.28 sine 50. So 0.28 sine 50 gives you, solving for F, you get 210 newton meters. That's your answer.